6 is 6. And so there we go. We have my we have our parallelogram here, and you would need to confirm, you would need to show me that it truly is a parallelogram by finding all of the slopes and say, hey, look, opposite sides truly are parallel. So the slope of this one is, I go up 2 and then over 6, so we have 2 6 and 2 6, but also check the other sides. Check the other sides as well. This slope is going to be negative, so I'm going to draw in my negative sign. My rise, I go from a 5 to 0, so that's negative 5. And then I go, my run, it goes from 5 to 6, so that's 1. And then just check it on the other side as well. And this is showing your work, you're ensuring that this truly is a parallelogram, which it asked for. So my slope over here, obviously it's negative because it's graphed, and then it goes from positive 3 to negative 2, so it's a negative 5, and then a negative 1 to 0, that's a positive 1. So there you go, opposite sides truly are parallel. You got yourself a parallelogram. I'm going to go ahead and do it another way. This is the same coordinates, but maybe you saw the vertex in a different place, like up here. If that's the case, then however I go from this bottom left vertex to the top left, I need to mimic that on this side. So how am I going to reach up here is do the exact same thing. So the slope of this side, I'm going to rise up 5 units. So I'm going up 5 units, and then I go negative, I go left 1 unit. So again, we get this slope of negative 5, so I'm going to have to mimic that over here. I went up 5 units, and then to the left 1, so 1, 2, 3, 4, 5, and then over 1. Whoops, didn't even draw that. And then negative direction 1 unit, that means to the left. And so you can see that this point is at 4, 10, and you have your parallelogram that looks like that. And again, you would have to just show the slopes and truly prove that it really is a parallelogram, just like I did in the previous example. And then for those of you who saw it the last way, this desk is squeaky. Maybe you saw the other coordinate point being out here. That's legit as well, so let's go ahead and find that. So I need to go to this bottom left vertex, and so what I'm going to do is I have to mimic the way I get from the top right to the bottom right. I have to mimic that here. So however I get from my top left to my bottom left vertex, those must be the same. And so I look here and I say, well, to get from this vertex to that vertex, I go down 7 units, 5 to negative 2, that's a negative 7 units, and then I go to the left in a negative direction, 5 units, so 5 to 0. So I'm going to mimic that exact same slope and distance on this other side. So I need to start here at my top left, go down 7 units, 1, 2, 3, 4, 5, 6, 7, and then go to the left 5 units, 1, 2, 3, 4, and 5. And so there I am. This would give me a negative 6, negative 4. That's where this coordinate point lies. And once again, you would have to show that this is a parallelogram by finding all the slopes of each side and showing that both pairs of opposite sides are parallel. Moving on to the next one. Tells us that this is a rhombus. Now we're going to have to take a different approach when we're trying to find the fourth vertex of a rhombus. There's only one answer for these. It can't be in 3 different positions. And the best plan of attack is you knowing the definition of a rhombus and you realizing that you know that all four sides are congruent. So this fourth vertex needs to be placed so that the all four sides are congruent. So you have you have three options of side lengths. This could be a side length connecting those two dots. This could be a side length connecting those two dots. And this could be a side length. Two of them are going to be sides of the rhombus, and one of them is going to be a diagonal. Well, we know that if this truly is a rhombus, then the sides need to be congruent. So what you need to do is you need to find the three distances of these segments here that I have dashed. And two of them will be the exact same. And so that will identify for you the two sides that you were given, and then you can continue to extend that that quadrilateral in that direction. So you'll see what I'm talking about. Let's find the distance of these. So I'm going to give myself the outline. I know that the distance formula is change in x squared plus change in y squared, and take the square root of that. So going from this point to that point, my x values, it goes from 4 to a negative 5. And so that's a change in 9 units. And then my y values go from a negative 2 to a positive 3. So that's a change in 5 units. Again, you can count that. How far do you go up and how far do you go to the left or right? So my distance for this is going to be 81 plus 25. So that's going to be 106. And again, I know that I could simplify this, but we're just trying to see if two segments are congruent. So let's just find the distance and keep it in unsimplified form and just save us time. And we need to save as much time on the test. So I'm going to move over to the other possible side length, and we're going to see what's happening here. So here is going to be my change in x. So it goes from a negative 5 to a negative 3. So it's a change in 2 units. And then it goes from positive 3 to a negative 4. So that's a change in 7 units. So the distance is 2 squared is 4. 7 squared is 41. So I got the square root of 53. Moving on to my last one. Going to give myself the outline once again. This is the change in x, this is change in y. So the change in x in this first parentheses, I go from a negative 3 to a positive 4. So that's a change in 7 units. And then I go from a negative 4 to a negative 2. And so that's a change in 2 units. The distance is equal to 7 squared plus 2 squared. It's going to give me that 53. So I can see now, it's easy for me to identify the two sides of this rhombus, and they are clearly this side and that side because they both have a distance, they both have a length of square root of 53. So I now know that I'm going to go ahead and draw in this segment with a solid line and say, okay, these are my two congruent segments. From there, I don't need this distance anymore, and I don't need this dotted or that dashed line, so I'm just going to erase it. We used that to determine what are the side lengths. So that segment that I just erased, that happens to be one of the diagonals of this rhombus. So now I can see that if this is one side and this is the other side, then that must force the fourth vertex to be out here so I can continue creating this rhombus. So now it turns into just a very similar problem as we had over here with the parallelogram. We need to mimic this distance and slope, how we get from the bottom left to the bottom right. We needed to mimic that from going to the top left to the top right. So I see here that to get to this vertex to that vertex, I'm going to rise up, go up 2, and then in a positive manner go over 1, 2, 3, 4, 5, 6, 7. So I'm going to go to the right 7 units. So I need to mimic this. Again, it's just a congruent triangle is all you're creating. I need to mimic that from going from the top left to the top right. So I'm going to go up 1, 2, and then move to the right 7 units. 1, 2, 3, 4, 5, 6, and 7. So this new coordinate is at 2, 5. And then you can go ahead and you complete this rhombus. So now you have to prove to me that that the coordinate you chose does create a rhombus. So you'd have to look at your slopes and distances. And there's a number of ways you can go about that. You can look at the slopes to prove that it is a parallelogram, and then use the distances to show that it's a rhombus. I'm going to take a completely different look at this. I'm going to prove that this is a parallelogram by showing that the diagonals bisect each other. So this is just a different route of proving that this shape is first a parallelogram, and then I'm going to show that it is a rhombus. So I'm going to show that these two diagonals have the same exact midpoint. And if that's the case, then that means that these diagonals bisect each other. So the midpoint formula is the average of your x's and then the average of your y's. So what I mean by that is the midpoint is equal to x1 plus x2 divided by 2, and then y1 plus y2 divided by 2. So you're just taking the averages of your x and the averages of your y's. So that's what I'm going to go ahead and do right now for these two diagonals. I'm going to do the one in red ink first. My two x values are a -3 and a +2. So the average of those is the sum of those is a -1. So -3 plus 2 gives me that -1. And then I'm going to look at my y values. It goes from -4 to a +5. So the sum of those, y1 plus y2, -4 plus 5 is a +1. So I can see that the midpoint of the red diagonal, I'll put this in red, is -1/2, 1/2. So I'm going to do the same exact thing for my diagonal that's in blue ink. I'm going to find the midpoint. So I've got the averages of my x and the averages of my y's. So first look at the x values. It goes from a -5 to a +4. So -5 plus 4, that gives me a -1. And then from 3 to -2, that sum is a +1. So I've just now shown that the two diagonals have the same midpoint. So you would have to write to me and say, diagonals have same midpoint, therefore parallelogram. Then you're not done, because you got to show that this is a rhombus. Well,